All right, folks, welcome back. And we're going to look at a lot of the problems that we've already done before, writing out the mesh equations the long way, which is your fallback. Make sure you can do that for when things get a little weird in a problem. That's the way you want to do it. It's a little more consistent. But if you want to be quick, or if I want to be quick, because we're going to be using mesh analysis for the rest of the semester as we look at theorems and things of that sort, we've got to be able to do analysis quickly and accurately, and I'm going to introduce you to a way to do that. Some textbooks are going to call it mesh analysis by inspection, or they have all sorts of crazy names for this. I just call it the shortcut because this is what enables me to do it really quickly. So there's no real name for it. If you go talk to somebody when you get a job and you go, "Oh, I'm just going to use the shortcut," they might look at you funny. That's what I call it, but who cares what I call things? You should. Okay, you're stuck with me. Welcome to my neuroses. Okay, so we've seen this problem before. This was the very first problem that we started out with, and we were trying to find VA. But in order to find VA, we had to find the mesh currents. Okay, this was the very first mesh problem that we worked with. And we even did it seat of the pants before that. So this is going to be the third time we solve it. We're going to find the same answer. But we're going to do it quickly. Or I'm going to talk my way through how to do it quickly. This is a problem that if I was in class and I was working problems with you, I can look at it and I can punch it in my calculator without writing anything down. And that's how I'm going to do it in 30 seconds. Okay, I1, I2. Label the mesh currents. Here's something important with the shortcut, if you will. Label all mesh currents. I wanted white, but we'll stick with orange. Label all mesh currents in the same direction. Okay. When we first started doing mesh, I said you can label them clockwise, counterclockwise, mix and match them all you want. You can do that if you're writing it the long way and you're being careful. But if you're using the shortcut, one of the things that makes us faster and more accurate is if we do things consistently. And the thing that we're going to do consistently here is label the mesh currents in the same direction. My habit is clockwise. Very quickly, my habit can become your habit as you watch me work a lot of these problems. But if you're like, I just like doing things differently, I can totally relate to that, by the way. I like to do things differently. But if you like to do things differently and you want to do them counterclockwise, fine, just be consistent about it. Okay, so label all the mesh currents in the same direction. That's an important one. Don't cross it out. Okay, I want to emphasize that. And then we're going to start by just writing the matrix. And that's what makes this fast, is we go right to matrix form. Okay, so this has two mesh currents. So we're going to get a 2 by 2. And I'm going to invert that 2 by 2. And I'm going to get a right side that's 2 by 1. And if I multiply that together, okay, then we get the vector of our unknowns. So rather than writing out all the equations, here's how we're going to do it. Okay, so I still have that plan in the back of my head. There's no current supplies in here, so I write no KCLs. So the equations that I'm going to write correspond to the rows in the matrix: KVL for I1, KVL for I2. So I am keeping that in the back of my head, that I am in fact writing KVLs. Okay, so looking at the KVL for I1, these are going to be the I1 coefficients, these are going to be the I2 coefficients. All right, so if I'm writing a KVL for I1, I say, what does I1 touch? Okay, and since that's the mesh that I'm writing the KVL for, I add up all the passive components, resistors in this case, and it ends up being positive. Okay, so 6 plus 24 is 30. And then I move over here and I say, okay, what does I1 share with I2? Okay, so what does this mesh share with this one? Only the 24. And since it's a shared current, look, it's going the opposite direction. Okay, so if I1 sets the positive direction, I2 is going against it, and it's negative 24. So that's why we always draw these in the same direction, so that the shared currents are always negative. And then what does I1 share with itself? If that's a question you can ask. That's a funny way to say it, but it's kind of how it works out. What does I1 share with itself? Positive 30. What does I1 share with I2? Negative 24. And then on the right-hand side, we move around and we look for any voltage drops. So I'm going up 24. That's a 21. I'm going up 21, and that's it. So this is going to end up being a positive 21. Okay, that one's done. With a little bit of practice, I'm hoping you see how you can do this very rapidly if you need to. Okay, move over here. Let's do the KVL for I2. What does I2 share with I1? Well, it only shares the 24, so I get negative 24. What does I2 share with itself? Well, it's not really sharing it with it. It's what does I2 touch? And that's the one I'm writing the KVL for. 24 plus 14 plus 10. So that looks like that's 48. Okay, the right-hand side, there are no voltage supplies. So I get a 0 on that side. All right, now if we solve that, grab your calculator and just punch it in. Okay, 30 minus 24 and 21, negative 24, 48, and 0. And from that we get hopefully the same result. It is the same result, 6, 7, as we did when we first started working on mesh analysis. This was the very first problem that we worked. 583.3 milliamps. Okay, now I have the mesh currents. I can go find whatever I want to find using those mesh currents. Here's VA, right? And VA was across there. VA is I1 minus I2 times 24, and that ended up being 14 volts. Same as the first time we did it. Okay, now to prove that to you, I'm going to pull up the notes from the first problem we worked with mesh analysis somewhere. I thought I had opened it. There it is. All right, and I'm gonna break the fourth wall here, and there's our notes from the first time we did this. And what did we find for mesh currents? Okay, 1.167 amps and 583.3 milliamps. Now let's grab that over to our pad. Okay, and I can place it right there, and they're similar. They're very similar, but you'll notice that we have sign differences. Okay, so this is from a previous video. Okay, so that's 30 and that's negative 30 and that's negative 24, and this is positive 24. If I take my equations and I multiply left and right hand side by -1, it ends up with the same equation, and then I'm going to end up with the same result because I haven't effectively changed that equation within the system. So what you'll find is if you do the shortcut, a lot of times you'll have sign differences. The point of this is that if one sign is different, they all have to be different. Okay, so this is positive 30, negative 30, negative 24, positive 24, positive 21, negative 21. Okay, so within each row, if one sign is different, they all have to be different. They have to be consistent. You can mix and match the rows. Some can have the same sign, some can have different. But as long as within the row the signs are consistently opposite, then you're in good shape. Okay, so if I was doing this quickly, and we're gonna start to move a little quicker with the next problems. If I was doing this a little quicker without explaining everything, then I hope you see that you can do this in 30 seconds. All right, couldn't do that before, and you're gonna get the right answer, and you're gonna get it consistently. That's the goal. All right, we got to practice. So let's go look at some of the other problems that we've already worked, but let's work them with a shortcut this time. Stay tuned and good luck.